All right, once you recognize that the total electric flux through the entire three-dimensional object is 0, then we basically have 5 sides here. The electric field is parallel to, or perpendicular to, the area vector for the end caps. It's perpendicular to the area vector for the bottom. So we have only 2 surfaces it's going through. So the electric flux is 0. So we have slanted top, I guess E, the electric, I don't want to do this, E dot A of the slanted top plus E dot A of the, whatever this side is called.
Yeah, it's the front.
Front, okay, there we go, of the front. So if we know what that is, we can solve for that. And so if we looked at that, because the electric field is perpendicular, to this side right here, or parallel to the area vector, that just becomes the electric field times the area of the front, times cosine of 0 degrees, which is 1.57 times 10 to the 4th times the area of the front, which is 1.1 times that length right there. And there are a couple ways of going about it, but tangent of 40 degrees is equal to, I will call this O over 0.5. And so this becomes 0.5 tan 40 degrees. This will end up with a positive version of that. And so the electric flux through the slanted top would be negative.
So that was the way the Helmer did it, right?
Yes. They did it the easy way, but we're better than that.
So that says tan 40, right?
Yes, it is. Any other questions from the homework? All right. Anyone need to borrow a calculator?
Sir, you gave me the wrong one.
Oh.
You gave me the flash.
You didn't want to do that a second time?
If it can count for this, I would do it.
Yeah, but you'd still only get 10 out of 20 points.
Yeah.
Anyone else got their own quiz? I guess they're special. We last left off with introducing you to the Nabla. And the relationship, more importantly, the relationship between the electric field and the electric potential. So, before I continue on, are there questions? Pardon?
Chapter 26.
Yes, chapter 20, yes, 26. All right, so we did the more generalized equation. If you're in a rectangular coordinate system, it looks like this. There's another version of it if you're in a polar coordinate system, and another version if you're in a cylindrical coordinate system. Well beyond the scope of what we need to do in this class, but just be aware it looks different. You've got some trig functions in there if you're dealing with polar or cylindrical coordinate system or spherical coordinate system. And again, I think you get that in Calc 3 at some point, unless times have changed. So if these are partial derivatives, this right here is the nabla, is a vector operator, and these are partial derivatives, and when you do partial derivatives, you assume anything that is not the letter in the denominator is a constant, so the partial derivative of xy with respect to x is just y, because you assume y is a constant. Here, you assume x is the constant because y is our differential, and we just get x. So I plotted out at least two equipotential lines for my equation for the electric potential. The electric potential is a function of x and y, and more specifically, it's x times y. And so you get these two equipotential lines, and more if you feel like drawing them. And I want to look at the point here, this point right there. This is the coordinate of 2, 1/2. So my electric field I am claiming is negative 1/2 I hat minus 2 j hat, because x is 2 and y is 1/2. If I plotted that, assuming I hat and j hat, now the assumption that I hat and j hat are in the traditional system or traditional coordinates is actually implied already. The fact that I have x here and I hat there tells me that I hat and x are, I hat is in the positive x direction, j hat's in the positive y direction, k hat's in the positive z direction. So if I plot it, I go negative 1/2 I hat, and then negative 2 j hat, so 1, 2, and it looks something like that. Now it's not drawn perfectly, but do note that that is a right angle there. Just as you were doing in the electric potential lab, the electric field is perpendicular to the equipotential line. If we take this point right here, this is when V is equal to 2, so this is the point 1, 2. My electric field at this point should be negative 2 I hat minus 1 j hat. Again, just plugging into this equation right here. So from this spot right here, I go 2 in the negative, 2 in the negative I hat, 1 in the negative j hat, and my electric field's pointing in that direction. And again, perpendicular. Now, it's much simpler if I'm only dealing with one variable. If V is a function of only a single variable, in other words, if it was just x, then, well, those will go away because there's no y, there's no z, so since everything else is a constant, those terms would drop out and you're left with just a simple derivative. And since x is the only variable, both the partial derivative and the normal derivative are the same. So if we are dealing with v as a function of r, then I can simplify it down to this. This is just the special case of a single variable. And we can confirm that's true for the case of the point charge. So v is equal to kq over r plus some constant. Which is kq r to the negative 1 plus some constant. And so the derivative of V with respect to R, negative KQ R to the negative 2. But my electric field is the negative of that, so this would become negative KQ over R squared, or KQ over R squared. Oh, I did leave something off here, R hat. And I probably should do that in the same color just to emphasize that it's not specific to this problem, there should be the unit vector there. And we get the formula that we pretty much started with. Questions for you? And I think they did this last time, not 100% sure. If I do a dot product, negative dV dr, r hat dot r hat. So do a dot product on both sides of this equation here. What's r hat dot r hat? I wasn't expecting the silence there.
One.
Yes. Dot product. Remember, it's the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. What is the angle between any vector and itself?
0.
And therefore the cosine is
1.
1. And the magnitude of the unit vector? 1. Yeah, that's why it's called a unit vector. Magnitude, so that's 1 times 1 times 1.
See, I've been thinking 1 earlier, I just wasn't completely sure.
You know, we're gonna all make plenty of mistakes in here, so just be bold, just go for it. Be hailed as a genius or a fool. You gotta be hailed as a genius or a physics student, you know. So now I can multiply both sides by dr, so it's E dot r hat dr is equal to dv. Let's put the negative sign over there, and then integrate. And since we're only dealing with a single variable here, E dot dr is equal to delta v. When you integrate both sides over here, we're integrating with just the differential, so it's just the change. So we have the other relationship going the other direction. Is equal to delta v. Now, if my electric field is constant, then this becomes E dot dr equals delta v. So again, this is electric field is constant in space. Not claiming whether the electric field is constant within time, but as long as it's constant throughout space, I mean, that can vary with time, but the important thing here is that it's constant in space. Now, with electric fields, this is not really a huge thing, but when we get to magnetic fields, then there are various times where it does matter. We're talking constant in space or constant in time. And so this is just negative E dot R is equal to delta V. So if I happen to have a positive plate here and a negative plate here, what's the direction of my electric field? Well, a couple people gesturing. my electric field, if these plates are large enough compared to the space between it, we can consider this to be, electric field to be constant. And so R is just the direction in which I'm going in. And so we'd basically end up with, if this distance here is, actually let's define the distance in this direction as D. Ugh. I can't bring myself to do that. X. Then we basically have negative E dot. What notation? I probably should settle upon a single notation here. Yeah, delta X. That's really not too revealing after that equation right there, but I was heading towards someplace. So if I'm going in the direction of the electric field, my dot product here, basically those are in the same direction. So this becomes negative E delta X is equal to my change in my potential, or otherwise known as voltage. So if I know this distance, I know what my change in potential is, and notice also that my change in potential, if I'm going from left to right, my change in potential is negative, which implies that the positive plate is at a higher potential than the negative plate, which actually, I think most people have an intuitive sense that a positive plate will have a higher potential than a negative plate. Many times in physics, it doesn't always make intuitive sense like that, even though it makes mathematical sense in this case. I think it does both. Questions at the moment? We will exploit that quite a bit in chapter 27. Whenever we get to capacitors. I should get some textbooks sneak it into the previous chapter and then do most of it in the next chapter. And it looks like that is, 27. One other exploration of this. Let's say I have a potential versus position. Oh, yes.
I was just gonna ask can you explain again how you went from R to delta X?
R is just the radial vector from whatever your sort of center of your system is. So if I'm considering this plate to be the center of my system, R is just a vector that's pointing away from it.
Okay. And
so I just, for some strange reason, suddenly decided to call it delta X.
Okay.
But it gives us the Vex equation. Ignoring deltas. A lot of textbooks, it's the VED equation, so that's why D initially popped up, but using D for distance just seems so common.
Okay.
We're better than that. Let's see how many different letters we can use for the exact same thing. Did it answer your question?
Yeah.
Okay. Other questions before I continue? So if this is my potential, my electric potential, what does my electric field graph look like? As a function of R. Well, basically it's the negative slope. So we do it bit by bit. Here my slope is relatively zero. It's close to zero, but it's still a negative slope here, so my slope is negative. But since the electric field is the negative of the slope, my electric field would be positive, and something small, something close to zero. My electric field gets more and more negative here. And let's write out that we're gonna just, how do I do that? Do it that way. So this is my slope of my potential versus R graph. My slope here gets more and more negative. So this becomes more and more negative, but the minus sign in front suddenly makes it more and more positive. And so my electric field graph is going to look something like that. And this region right here, my slope is still negative. It starts out incredibly negative and becomes less and less so. So my slope is negative. The negative of my slope is positive. So again, this is some positive number. At this point right here, my slope is zero, so my electric field is zero. Over here, my slope is positive, going from something small to something huge. And so I want the negative of that, so it goes from something small to something huge, negative. And then over here, my slope is negative. And since the electric field is the negative of that, it's positive. And so that's what it's a rough sketch of what my electric field looks like. Yes?
Could you explain that again? Like, why is the, on the far left side, it's like the inverse of the graph above, and then on the far right, it's not?
All right. So my electric field is the negative slope of my potential graph. All right. So my slope here is negative the entire time. Since my slope, let's narrow that down some. That's my slope, so it's the negative of my slope. Since my slope is negative the entire time, my electric field is positive. That's why this is on the positive side. Over here, again, my slope is negative the entire time, so therefore my electric field is positive. And then in terms of asymptotes, my potential, the slope is zero, close to zero around here, so my electric field will be close to zero around there. Over here, my slope is close to zero here, so I'm going to be close to zero here. That's where that comes from.
Okay, yeah, that's it.
So, if I have a conductor here, conducting sphere, and Q of the sphere is positive. So my net charge is positive. I'm going to set up a coordinate system here. So let this be my electric field, and R. Where are my charges? Let's assume it's an electrostatic equilibrium. Sorry, again?
On the surface.
All right. So and what is my electric field inside?
Zero.
Zero.
All right. And then suddenly, when I get to the surface, there's a spike there, and that's just gonna be KQ over the radius of the sphere squared. Once I'm outside the sphere, what does my electric field look like?
Positive.
Okay. And?
Does it decrease?
It does. If I'm outside a sphere or I'm outside of something with spherical symmetry, charge distribution symmetry, how do I treat this?
A point chart.
Yes. So if I'm outside of it and it's a conducting sphere, electrostatic equilibrium, you got the symmetry, I'm treating it like a point charge, and it's just a 1 over r squared relationship.
Mhm.
My potential, I know is the negative integral of E dot dr. So let's think about the area. I need to establish where is delta V. I need to establish where my potential is equal to 0. Because that will make a huge difference in how I'm shifting my graph. So let's go with a traditional, that my potential equals 0 when r equals infinity. So my potential, out here is somewhere small. And let's just start sort of figuring it out. I know that as I move this way, that my that's the area under my curve. The area under my curve is increasing as I move this way. And that negative sign's gonna mess me up right here. Oh, because I'm going backwards. Yeah. Let's take a moment to think about calculus. The integral from 0 to 1 of x dx is, well, I got 1/2 x squared from 0 to 1, which is 1/2 minus 0, which is 1/2. I hope this is not a shock to anyone. The integral from 1 to 0 of x dx is
-1/2.
so suddenly I'm doing my integral here and I'm going backwards, and we're gonna have like a double negative going on. So my electric field, as I'm going to the left here, is getting bigger and bigger. Now the negative would make it seem like therefore it should be getting more and more negative, except for the fact that I'm going backwards here. I'm going opposite direction of dr, which is typically in that direction. And so it's gonna get more and more positive until I get to here. We're gonna work it backwards in just a second to double check. And then my area does not change one bit. So therefore my potential, once I get to the surface, becomes constant. Everything inside my sphere there is at the constant potential. Now we double check, let's go back the other direction. So my slope here is 0. Oh, Lawson?
Everything inside the sphere has like the constant potential is equal to the greatest potential?
It's equal to the potential at the surface,
Okay.
which in our simple scenario here is the greatest value. But, I mean, I can come up with those scenarios where, think of it, whatever it is at the surface, that's what it's gonna be.
Okay.
So my slope here is 0. And my electric field is the negative of that slope, and so this would be -0. let you philosophically decide if positive 0 and negative 0 are the same number or not. Or are they just two numbers with the same value? And then, in this region right here, my potential curve is a negative slope the entire time. And therefore, the negative of that slope would be positive, and so my electric field should be positive the entire time. And so, double check going back the other way just to make sure. The negative 0 bit goes back to a PSAT question that I had a friend and I both missed it, because it came down to whether negative 0 and positive 0 were the same number or just two numbers with the same value. And there was a proof we had done in pre-calculus to show that negative 0 equals positive 0, which to us implied that they are not the same number, they just have the same value. So we both missed this question, which probably most people got.
That's a PSAT question?
That was a PSAT question. It came down to whether negative 0 and positive 0, again, same number or just numbers with the same value. Two different numbers with the same value. I think we overthought that one. All right, at this point, let's put a nail in the coffin of 26. So what I'm thinking here, well, here's the bit, because I'm about to start into the material for the next test, for test 1B. There was a semester where I finished all the material for test 1B before we actually had the test for 1A. This happened one semester. I've gotten most of the way through the material for test 1B before students have taken test 1A. And I don't know how much it messes the students up, but we could do the quiz on 26. When do you want the test? I think that's what it comes down to.
Never.
Today's the night. Is that a never? We could bring it all down to just your big chunk of your grade depends on one test that you take at the end. I'm not a real fan of that one, but hey, you are the 6 that are here. You can decide for everyone else.
Do you want it on the Tuesday or a Thursday, the test?